and their sum is 1. So then, the textbook answer is that the probability of, well, if a state is in, if you're observing a system that's in a state psi, the probability of an outcome, sigma, is p sigma, is the expectation value of the state in the state of the projection operator onto outcome sigma. And if you observe sigma, then the post-measurement state is, well, it's pi sigma times psi, except that we have to normalize it. Which I think means dividing by the square root of p sigma. So the sum of the p sigmas is 1, because the sum of the pi sigmas is 1. Now, I stated this for pure states, but if the system is in a mixed state, rho, then, well, we can get the answer for density matrix just by writing this formula as the trace. We just replace the projection operator into the pure state by any density matrix. Well, this is the motivation. But the answer, if the system is in a pure mixed state rho, is that the probability of the outcome p sigma is the expectation value of pi sigma in the mixed state rho. And the post-measurement density matrix will then be 1 over p sigma times pi sigma rho pi sigma. So, well, this is a quantum measurement, at least as I learned about it as a student, and probably most of you. However, it's not the most general thing one can do. So let's call the system B, and we'll let C be an auxiliary apparatus. Sometimes call it an ancilla. And what we do is we initialize C in a known state. I'll call it 1, or 1C. Let's say that C has a basis of states KC, where K runs from 1 to n. So C is a quantum system with n states, but we initialize it in one particular known state. So, well, I'll describe this as initially assuming that the system B under study is in a pure state. But as in the previous case, we can immediately generalize it to mixed states. So we start with the system CB in the state where C is in the known state 1 and B is in some state psi. Then we act, well, what can we do when we act on a quantum system? Quantum systems evolve by unitary transformation given by the Hamiltonian. The Hamiltonian might be time-dependent, but the exponential of a time-dependent Hamiltonian times I is still a unitary operator. So all we can do when we act on a quantum system is to apply a unitary operator. So we apply a unitary operator, which we do by manipulating possibly a magnetic field or in some other way controlling the Hamiltonian that governs this system. We so we find a unitary operator U on system CB, which we choose so that UCB on 1C tensored with any state of B is the sum from k equals 1 to n of the state k of system C tensored with some matrix EK on system B. So that's the most general thing that any U could do to states of this kind. It would map system C from state 1 to some state k, and meanwhile it applies some linear transformation to system B. So there's certainly no loss of generality in assuming that U acts that way. Instead, there's a constraint of unitarity. So we want UCB dagger UCB equals 1. And that will tell us that, well, UCB on 1C tensored with psi 1 is equal to, let's say, I'll assume that psi is a normalized state. And that means that our initial state is normalized. And that means that we should still get 1 after we act with UCB. So the right-hand side, which is supposed to equal 1, is actually the inner product of two states. One is the sum over k of k tensored with EK psi. And the other, well, the same thing. The other is the sum over L of L tensored with EL psi. I hope this way of writing it isn't too confusing. That's supposed to equal 1. Now we take the inner product on the C system. The states K are assumed to be orthonormal. I probably didn't quite say that, but that was assumed. So the sum over K and L collapses to a single sum over K, and we get the inner product of EL psi, sum over K, of EK psi with EK psi. Or in other words, we get the inner product of psi with the sum over K of EK dagger, EK psi. So unitarity implies that the sum over K of EK dagger, EK, is equal to 1. And there's no other constraints. If you take any EKs at all that satisfy that relation, then there's a unitary matrix, a unitary operator, that will act, as I've written, on states where C is initialized in state 1, and will do something else to other states. I won't try to prove that for you, but you can think about it later if you wish. It's not difficult. It amounts to saying that if you want to construct a unitary matrix, as long as the first column is a unit vector, you can complete any unit vector to a unitary matrix by completing this one vector to an orthonormal basis. So the statement that a U that does this, okay, more generally, if I give you any set of columns of what's supposed to be a unitary matrix, and they're orthonormal, they can be completed to a bigger set of orthonormal vectors that will be a basis, and that'll give you a unitary matrix. So that's the idea of why any such U, well, for any set of E's, this formula can be completed to a unitary operator. So there's absolutely no constraint on the EKs except this one. Now, to make our measurement of system B, what we do is we first combine it with system C in this boring way initially, but then in this more interesting way by applying unitary. And now we make a projective measurement on system C using the projection operators pi k, which is just the projection operator of system C onto the state k. Or, maybe I should say we use the operator pi k times 1 on B. So these are projection operators on the joint system BC. And these projection operators satisfy all the conditions we stated at the beginning. They're orthogonal, commuting. So when we make a projective measurement using these projection operators, we're back in the case that the textbooks definitely told us about at the beginning of making a classical measurement with commuting orthogonal projection operators that add to 1. Well, so now the outcome, the probability of outcome k is the expectation value of pi k in the state. The state being this thing. So it's the expectation value of pi k in the state, which is the sum over k of k tends toward ek on the initial state of system C, of system B. Well, I don't know whether on the left I should write bras or cats. It's a little bit ugly looking either way. I hope what I'm saying is clear, though. We want to take the expectation value of pi k in the state that was the output of this unitary transformation. When we do that, we get the same calculation as before. Sorry. I shouldn't have. The dummy summation variable here shouldn't have been k. That k was the label on the projection operator we're evaluating. So the part of the matrix element on system C is just the expectation value in the state L of the projection operator onto k with the initial state being m. And that's just a Kronecker delta. It's 0 unless m and l are both equal to k, and otherwise it's 1. So these sums all go away. And this probability of outcome k is just the expectation value, well, it's just the inner product of ek psi with ek psi. Or in other words, it's the expectation value in the state psi of ek dagger ek psi. And now we note that we have this handy identity from unitarity, which tells us that the probabilities of the outcomes add up to 1. So we've arrived at the idea of a generalized measurement. So instead of picking orthogonal projection operators, orthogonal commuting projection operators on the state, we pick any measurement operators, EKs, such that the sum of EK dagger EK is 1. And then we can make a measurement where the probability of the kth outcome is just the expectation value of ek dagger ek in the state. Now, I explained this for pure states, but the outcome of this, see, if you want to understand how to write it for a mixed state, what the answer is for a mixed state, you just write the pure state formula in terms of a density matrix, and the generalization of that, well, this is equal, but the generalization is the trace of the density matrix of system B times ek dagger ek. The reason we know this generalization is correct is that any rho B is simply the sum of, and there's going to be no, saying that the system is in a mixed state just means with some could be interpreted to mean that with some probability qi, it's in the state psi I. So that means that we just have to average over these answers with psi replaced by psi I and with probabilities qi. But that will just tell us to replace this by a general density matrix rho B. So a formula like this, once you write it in terms of the pure state density matrix, automatically generalizes to any density matrix. So what I've described is really the most general measurement you can make of a quantum system. You don't, in general, use commuting projection operators. You use any operators, ek, who's such that the sum of ek dagger ek is 1. Any questions on any of that? Okay, good question. The question is, what's the final state after we made the measurement? Yes, up to normalization, the final state will be ek on psi if we started with the pure state. Because what we did was we had the sum of, this was the joint state of system BC. Then we applied the projection operator. Well, this was the projection operator, the kth projection operator of pi BC. I shouldn't call everything k. Let me call this n. Then by the general rules, if you make what we did on the combined system was to make a measurement in the traditional sense with projection operators. So the final state after the measurement, if you get outcome k, is just the initial state projected onto outcome k. So it would just be k tensored with ek psi, except that you have to make it normalized, which I guess means that. So if you, since the auxiliary system C is in a definite state after the measurement, you could forget about it. If you're just interested in the original system, you'd say that the original system is in the state ek psi after the measurement. That's assuming it started in a pure state. The mixed state version, well, first, to deduce what it is, just write this first in terms of density matrices. So you'd say the final density matrix is this. But that would be true whether or not the system was initially in a pure state. So the generalization of that if the system B was originally in a mixed state described by density matrix rho B, then after the measurement, if the outcome of the measurement was k, it will be in this sense described by this density matrix. And the trace of that density matrix is indeed 1, because pk was the trace of rho B times ek dagger ek. So this thing has trace 1.
On that case, the right-hand side wouldn't just be the combination of the left-hand side, right? Because of the pk factors there.
What did you say? Say it again?
The right-hand side, like on...
This?
Yeah.
No, sorry. We're looking at, now we average over the initial states. We keep the final state k fixed, but we average over initial states. So we assume that the system was not definitely in the state psi at the beginning, but it was in some states psi I with probabilities qi. And that kind of incoherent averaging of what the initial state was just carries over here. So we can replace. It wasn't important that the initial state density matrix was pure.
Yeah, but I'm saying just because of the 1 over pk factor there.
Yes.
If we just did the average of the left-hand side, we get something more complicated than right.
But we didn't average it. I didn't sum anything over k.
Okay.
I took the trace over system B. Well, I wanted to make sure this was a density matrix. So to be a density matrix, the trace of this operator has to be 1. And then I remarked that since pk was defined this way, it's true that the trace of this operator is 1. We didn't do any summing over k in that statement. Any other questions? If there aren't questions, I think I'm not going to say more about generalized measurements. Let me see what I was supposed to say. Well, there's one more thing which we should say because there's one more thing which we should say partly as a lead-in to the next topic. So, okay, here we made a measurement and we observed the outcome as being k. But something else we could have done, which is after applying this unitary operator, either before or after making the observation, we could just throw away the auxiliary system C. And if we don't observe C, or don't care about it, or just throw it away, what is the final state of system B? Well, I wish I had a convenient formula written on the blackboard to write that down, deduce that immediately, but I don't quite see it. Well, okay. What the question means is we have this state. Well, okay. That's written for the case that system B was initially in a pure state. So we will make the usual substitution to mixed states at the end. If system B is originally in a pure state, so after applying the unitary, system BC was in the state sum over M of n tensor em psi. Now, it actually doesn't matter whether we observe M or not. If we just throw away system C before or after observing M, or we simply decide to forget about system C if we don't care about it, then we have to take then we have to take the reduced density matrix of system B. So the way we do that, as usual, the density matrix of system B after applying U is going to be the trace over C of If system B was originally in a pure state, then after we apply the unitary, the combined system is still in a pure state. But system B by itself will be in a mixed state, and we find that mixed state by taking the trace over system C. That means we trace over the unobserved state of system C, and in this case, the partial trace just gives the sum over M of Em psi times Em dagger. I wonder if I should go over that more slowly. So psi BC times psi BC, we could write as the sum over M and R of M R of system C times EM psi I think that's a better way to write it for system B. I've just written out in detail the pure state density matrix of system BC, taking this pure state. Then we're supposed to take the partial trace over C, that means setting M equals R. So set M equals R and then forget about system C. So we get just a single sum of EM and the generalization of this, if the initial state was mixed, would be the sum over M of EM rho EM dagger. So if we set up the situation for the generalized measurement, but we don't care about, or we don't make the measurement, we don't observe it, or we simply forget the answer, system B ends up in this state. Well, what is true is that if we want to check that this is a density matrix, that will work. So is EM rho, the sum over M, EM rho, EM dagger, a density matrix? Well, it's obviously positive because its expectation value in any state the expectation value of rho in any state is non-negative. So the expectation value of this operator in any state is non-negative. So it's non-negative, so to make it a density matrix, it has to have trace 1. The trace of the sum of EM rho EM dagger, using the cyclic property of the trace, it's the sum over M of the trace of rho EM dagger EM. But the sum of EM dagger EM is 1. So the underlying unitarity enables us to prove that the new density matrix, in fact, is a density matrix. But it doesn't tell us more. It's not equal. It's not the case. I used unitarity, and what it proved was that the new density matrix is a density matrix. It didn't prove anything else, because the only property that the E's have is this. To get the identity, we'd have to move the EM dagger over here. Because the only unitarity only tells us that the sum of EM dagger EM is 1. But the EM dagger is acting here, and EM is acting here. So we can prove that unitarity tells us that the probabilities add to 1, but that's all it's going to tell us. So actually, what we've just done answers a question I hadn't asked yet. Well, oh, sorry, I won't ask it quite yet if there are more questions.
So do we need like another condition for EK, like summation EK dagger is 1, or like this is enough?
No, this is, well, I'm hoping that from the explanation it would be clear that this is the only condition. So I did derive that this condition was necessary. And then to show that it's sufficient, we need to know that there does exist a unitary operator that maps, that does what we said. So I proved that for such a U to exist, this has to be true. I didn't quite prove the converse, but I kind of told you how to prove it. In general, if I give you a bunch of columns of what's supposed to be a unitary matrix, maybe in this case I should have called it a bunch of rows. I told you what the unitary matrix did on some states. So I guess that's equivalent to telling you a bunch of rows of a unitary matrix. What we checked was that the rows I gave you are orthonormal. Then, hopefully you know from linear algebra that any set of orthonormal vectors can be completed to an orthonormal basis. So you add more rows, making an orthonormal basis, and at that point you have a unitary matrix. So that's how you're supposed to prove that the condition that we imposed is the only one. Any other questions? So as I started to say, this formula here is actually an answer to a question I didn't ask yet. So let's ask the question, and then eventually we'll arrive at that answer. Okay. So, first of all, the subject goes by the name of quantum channels. So the question we ask is, what's the most general way to manipulate a quantum system? Well, if the quantum system is isolated from the rest of the world, it will evolve by a unitary transformation given by its Hamiltonian. You can control the Hamiltonian by, for example, adjusting external magnetic fields. If you have a spin system, by changing the magnetic field, you change the effective Hamiltonian of a system, and therefore the unitary operator by which it evolves is somewhat under your control. So the most obvious answer we can act on a quantum system with a unitary operator. However, let's discuss some things you can do to a quantum system that don't involve acting with a unitary operator. Suppose I give you a quantum system in an unknown state, and you want to put it in a known state. For example, I give you a spinning half particle, and you'd like it to have spin up along the z-axis. How can you achieve that? Well, there's no unitary operator that will do the job, because there's no unitary operator that will map any state of a spin half particle to the z-axis. To spin up along z, or to any preassigned state. So clearly we can't put a quantum system in a desired state by a unitary transformation, if we don't know the initial state of the quantum system. However, that doesn't mean we can't put a quantum system in a desired state. One way to do it is to apply a magnetic field such that the ground state is spin up in the z direction, and wait till the system relaxes to its ground state. Another way to do it is to measure the spin along any axis. After you measure the spin, you know what state the system is in, and then you pick a unitary operator that maps that state to spin up along the z-axis. Now, neither of those operations were simply applying a unitary transformation. And in each case, there was some additional system that played an important role. In the first case, we applied a magnetic field. And we can think of that as coming from manipulating a C-number external field, so there's no quantum system necessarily involved. But then we had to wait for the system to decay to its ground state, which it did by somehow emitting energy to the environment. It emitted a photon, perhaps, or it exchanged energy released energy to a nearby atom or something, but there was some other system involved. And when we made the measurement and then applied the unitary, the measuring apparatus was important. And it got into a final state that depended on the measurement outcome. So in each of those two examples of how to manipulate a quantum system by something other than the unitary transformation, there was some other system involved. And another example is that you might have a system in a possibly unknown state, which might be either pure or mixed, and you'd like to put it in a maximally mixed state. Well, how can you get a system in a maximally mixed state? Well, that's regrettably easy to do, all too easy to do in the lab. You just let your system interact with a noisy environment for long enough, and it will be in a maximally mixed state, which you know nothing about. But there's no transformation by unitary evolution that will map, well, a non-maximally mixed unitary evolution will transform always a density matrix by conjugation. So, sorry. On a pure state, unitary evolution just means we act with a unitary operator. So on a pure state density matrix, unitary evolution is like so. And that's the kind of formula that automatically carries over to mixed states. So a maximally mixed density matrix is a multiple of the identity. And if rho isn't already a multiple of the identity, conjugating by u won't make it one. So we can't, by unitary evolution, change a density matrix to a multiple of the identity. But letting it interact with the noisy environment will do so all too easily. So a lot more evolution of a quantum system is possible than can be achieved just by unitary evolution. But more general evolution of a quantum system requires interaction with another quantum system. That was clear in the examples I gave where the other quantum system was either a measurement apparatus or else the environment. And I've actually already told you about the most general possible evolution of a quantum system. The most general possible evolution of a quantum system can be described by 3 steps, which are very similar to the steps we already invoked when we described generalized measurements. So I'll call the quantum system B. Step 1 is to combine B with another system C in a trivial way. I think I'll write this to begin with, assuming that B might be in a mixed state, rather than starting with pure states as I've done in the other examples. So the first step, we replace rho B with the density matrix of system BC, which is just a known pure state density matrix of system C, tensored with rho of system B. That was step 1. Then step 2 is to apply a unitary UBC. So this maps rho BC to UBC then step 3 is forget system C. That is, take a partial trace. So this maps, well, I don't want to rewrite this, so I'll just call it this maps the expression we have here, I'll call it just Z, maps Z to the trace over C of itself. So that's the final density matrix of system B after the measurement. But now for U, without any essential loss of generality, we can take the U that we've been using. Unfortunately, I seem to have erased it. So since we applied U to a state where system C was in state 1, there's no loss of generality to assume that UCB takes the form we've been assuming, or that we've been discussing. And then if we use this for UCB, we'll find that although we got to it in a slightly different way, the density matrix after all this is just what I called rho B after before, which was the sum of EM, rho EM dagger. So that's the most general possible evolution of a quantum system. And in this context, the EMs are called cross operators. So I only proved that it was a possible evolution of a quantum system, not that it was the most general. You can find, I don't remember quite if it's in Prescoll's notes, but you can find in more abstract treatments a proof that this is the most general possible evolution. But the physical steps are natural. Well, we couldn't get any non-unitary evolution except by combining with some quantum system, so we did so. And then we allowed unitary evolution, and then we threw away the auxiliary system and concentrate on system B. Anyway, so I'm not planning to try to give an abstract proof that this is the most general possible evolution, but it is the most general possible evolution of a quantum system. Any questions about that? So this most general evolution is called a quantum channel. So A quantum channel is a linear operator on density matrices that preserves positivity. It preserves positivity in a slightly stronger sense than I've explained. But I did show that this matrix is positive when we verified that it was a density matrix. Probably we've erased it. In general, no. So in general, the question was if it's possible to have a non-trivial relation. In general, you can have many. In general, the same operation can be written in different ways. So the EMs in general are not unique. And that's analogous to the following. A density matrix can always be written like so. And if you ask for the psi I to be orthonormal, then they're unique up to phases. But if you don't ask for the psi I to be orthonormal, oh, sorry. That's not true. Sorry. I'm not sure what, I'm dreaming. If there's only one psi, then it's unique up to a phase. But if the formula has different psis, this representation is not unique. You actually have a homework problem where you're supposed to exhibit the non-uniqueness in a case. And similarly here, in some situations there might be a most economical set of E's which would be as short as possible. But in general, there are going to be a lot of representations. Yes?
I think you assume that your E's are non-singular here. Doesn't that give you that it's unique?
I didn't assume that the E's were invertible. Non-singular means they have no zero eigenvalues.
But we brought it about from the unitary.
No, this is our only constraint. So the individual E's can have zero eigenvalues. Only their sum is 1.
Right.
But even if we assume that the E's are invertible, I'm quite sure that in general they're not unique. See, if you don't want to have too many E's, then it's hard to find them.
There definitely is a case where you can have as many as you want, but with the unitary evolution picture, where you throw out the other system that we
No. There's no constraint on the E's except that their sum is 1. And you see, you can have a quantum system with an n-dimensional state space, B, but the auxiliary system C could have been much bigger. So the number of E's can be vastly bigger than the size of the quantum system you're studying. So,
larger.
what?
It's not just the purification of B. We're not just doubling B then.
There was nothing in the lecture that had to do with any doubling of B. C was a completely arbitrary auxiliary system. There was absolutely no condition on the number of the E's or any other property of the E's except this relation. So we could have a spin-half particle. So a rho is a 2 by 2 matrix. And this is a relation among 2 by 2 matrices, so this is only 4 equations. But the number of E's can be 1,000,000. So this is only 4 equations for 1,000,000 variables. Well, for 1,000,000 matrices. So 4 equations on 1,000,000 matrices is nowhere near determining them uniquely. And asking for them to be invertible won't be any significant constraint. Yes?
Like instead of EM, we can take like EM by square root 2 and 2 copies of that. That would be the same. Or does that count as a counterexample?
Counterexample to what?
Can be written like differently or not? But you said number of EMs, we don't care.
Well, I didn't understand the question. Ask again.
So instead of taking like EM, like E1 through EK, let's say.
Yes?
Let's take like E1 by square root 2, but like twice.
Oh.
Same copy.
Oh, yes. We can do that, yes. That's a trivial counterexample, right. So what's being said is that we could replace E by E over the square root of 2 as one of the E's, and E over the square root of 2 as another E. And then that'll satisfy this in a trivial way, but that will be by no means the only way to satisfy it, because it's a highly underdetermined equation. Any other questions? Yes?
So in all the 3 steps, we never use measurements anywhere, but is the claim that measurements are also quantum
well, see, the quantum channel was closely related to the generalized measurement that we explained before. So the answer is going to have to involve reminding you of that. It depends what you mean by a measurement, because if you have a particular measurement outcome, well, the quantum channel that's so this evolution is what you get if you don't look at we described a generalized measurement that involved the same ease. It was the same thing except that you care about the final state of the measuring apparatus. So since you do, the final state has to be described as a state that includes the measuring apparatus. So you could call it a quantum channel, but it's not a quantum channel that acts on system B. It's a quantum system that acts on system B together with C. Yes?
So if we want to think about the evolution of rho over time, should we be thinking about these EMs as time-dependent operators that smoothly conform into?
Well, if you want to make this time-dependent, you need to do something called the Lindblad equation. And it requires some assumptions. So the Schrodinger equation with a time-dependent Hamiltonian possibly is rigorously valid microscopically from the point of view of non-relativistic quantum mechanics. But a continuous time-dependent version of this is not rigorous and requires assumptions. It's valid under certain conditions. It's called the Lindblad equation. I think you can read about it in Prescoll's notes. I wasn't planning to describe it. Yes? So it is important, but it's not universal. Yes?
But yes.
The reason, sorry, let me interrupt. So the reason is that there was a step here, which was the partial trace over C, which isn't really a smooth time-dependent operation. So when you try to make a smooth time-dependent story out of this, you have to imagine that there are a lot of degrees of freedom in the environment that you're interacting with, and you're constantly losing contact with some of them. And there are approximations involved. So there is a time-dependent, there is a version of this for continuous time evolution, but it's not completely general. Yes?
I think I kind of answered those. Just what was the assumption we made that like limited us not to simulate continuous time evolution? That because like at least naively for me, since that if you take one of the matrices close to the identity and the other one is like very small, you could simulate quantum time evolution.
Well, you could make this evolution be small if one of the EMs is close to the identity and the others are small. So yes, under some conditions. That'll probably be a special case of what I was just saying if we think about it more carefully. Or maybe it will lead to what I was just saying. Under some conditions, you can write an equation for continuous time-dependent evolution. That's an approximation to this story. As I said, the Lindblad equation. Any other questions? So in the classical case, we had a combined system xy with two probability distributions, pxy and qxy. And we proved monotonicity of relative entropy. That the relative entropy of p xy to qxy is equal to or bigger than the relative entropy of px to qx. And it had a clear intuitive meaning that relative entropy measures how hard it is to show that hypothesis Q is wrong, if that's actually the case, and P is correct. And it's harder to disprove a hypothesis if you observe only X than if you observe both X and Y. Now, in the quantum case, we instead would have system A and B with two density matrices, rho AB and sigma AB. And I asserted, but didn't yet prove, that the same analogous result holds. So I will give a kind of proof in later lectures, but at least equally important. I'll try to help you understand why it's important in later lectures. It actually has the same physical interpretation as classically, which is that if your hypothesis is sigma but the right answer is rho, then the relative entropy measures how hard it is to learn that your hypothesis was wrong. However, it's much harder quantum mechanically than classically to explain that statement. And although it's explained in my lecture notes, I'm not going to do it in the lectures because it would interfere with getting to black hole thermodynamics later. However, in both cases, what I've asserted is not the most general statement. It's not the most general version of monotonicity of relative entropy. So in the classical case, here we consider just forgetting system Y. Sorry, I forget what it's called. In the classical case, we could look at a general stochastic map. So a stochastic map takes a probability distribution as input and produces another one as output in a physically sensible way, which means that there are probabilities for transitions in different directions. And the most general classical statement, so we actually proved in one of the lectures this version of the statement of monotonicity, but there's a more general classical statement for a general stochastic map, and I'm not going to prove that. However, we will prove the general quantum statement. Which is a general quantum channel. So the general quantum case, well, the classical case can almost certainly be deduced as a special case from the quantum case by taking everything to be diagonal. But I haven't thought about that carefully and won't present it. But in the quantum case, we have one system, and it has two possible density matrices. Let's say rho b and sigma b. And therefore it has a relative entropy of rho b relative to sigma b. And now we apply a quantum channel. So that maps rho b to the sum of em rho b em dagger, and it maps sigma b to the sum of em sigma b em dagger, which I'll call rho b tilde and sigma b tilde. And the general statement of monotonicity of relative entropy is this. So I do want to explain that this statement follows from the version that we've already proved. Oh, sorry, not already proved, already discussed. So I do want to explain that in the quantum case, the more general statement follows from what we've already discussed and will eventually prove. Maybe not for 2 weeks. Well, we'll sort of prove. Some of it will be left as a little bit of reading you can do. But I hope to convince you that give an argument that will convince you that it's true, at least. Whether we'll prove it depends on a little bit on your standards of mathematical proof. So anyway, given this, how would we deduce that relative entropy goes down under any quantum channel? Well, we'll just look at the 3 steps. The first step, so let's just remember what's a quantum channel. The first step transforms rho b to and does the same to sigma b. So this has no non-trivial effect on the relative entropy. Sorry. My convention is to write a double vertical line for relative entropy because the single one is conditional entropy. But I've been forgetting that. Okay. So the first step had no effect. That should be obvious physically because we've done nothing. We've just accepted that there's another state in the system C in the universe in some state 1. But that can't possibly influence anything interesting we'd say about system B. If you like, though, you can look at the definition of relative entropy as the trace of rho log rho minus log sigma, and see that replacing these guys with these guys doesn't affect the relative entropy. The second step was unitary evolution. Let's call this thing rho hat b, and this one sigma hat b, just as an abbreviation. The second step in a quantum channel is unitary evolution. Sorry. These are joint density matrices on the combined system B and C. The second step was unitary evolution that takes rho hat BC to UBC, rho hat BC, UBC inverse, and similarly for sigma. But unitary evolution also does nothing to relative entropy. That follows immediately from the definition as a trace. If I take rho to rho U inverse, sigma to U sigma U inverse, then rho log rho minus log sigma will do the same thing. And that won't affect the trace. So the second step of unitary evolution also doesn't affect the relative entropy. And the third step was a partial trace. Forget C. And the partial trace is the one that I asserted at the beginning causes the relative entropy to go down. Or, well, that's an inequality. A more precise statement is it doesn't go up. Let's say it can only go down. It can't go up. So the structure of a quantum channel is such that the only step where the relative entropy changes is the partial trace at the end. And therefore, if we know that relative entropy goes down under partial trace, it goes down under any quantum channel. Any questions about this? Now, I haven't proved for you that it's true that relative entropy measures how hard it is to disprove a hypothesis. As I said, we won't do that. You can read about it in my lecture notes if you wish. But if we knew that, this statement would have been a consequence. Because if we're trying to prove that, if we're trying to disprove the hypothesis that sigma b is correct, an initial step could be to apply a quantum channel. And there'd be a contradiction if that made the relative entropy go up, because then we could have more easily disproved the hypothesis by first applying the quantum channel and then studying sigma tilde b. So the statement about the physical interpretation of the relative entropy, which we're not proving, we will in another way understand monotonicity of relative entropy later. But if we had established the statement about the physical interpretation, that would be one way to show it. Any questions on that? So we still have about 12 or 14 minutes today. And, well, on Thursday we'll start with a completely different type of stuff. I wonder if I should tell you, okay. Okay. We'll go in a different direction Thursday. Part of it will involve discussing algebras that you can read about in my article called Why Does Quantum Field Theory and Curved Spacetime Make Sense, and so on. But much of that article won't be relevant to the lecture. Anyway, since we have about 12 or so minutes today, I want to discuss one more topic that's more related to what we've been saying. And the reason I'm discussing this topic is the following. In the classical case, things like conditional entropy and also mutual information had clear meaning. For example, we argued that IXY measures how many bits of information you can learn about system X if you observe Y. Now, in the quantum case, we made formal definitions that were analogous. But I haven't proved anything about what those formal definitions really mean. And that's very subtle and not so easy. And I at least wanted to give one example where one can show that a quantum definition has an interpretation that matches its name. Usually, to prove such things, you need to use monotonicity of relative entropy, and that will be true in the case we will discuss. So I'm a little bit sorry to only give one example of illustrating what the quantum definitions really mean. And there is some more of it in the last section of my lecture notes, but time will keep us from giving more than the simplest example. Let's first consider a classical setup. Alice sends a message with n possible values. How many bits of information can she send? Well, Bob receives the message. He learns one of n possible answers, so the maximum number of bits of information he can get is log 2n. If you want to state this in a very formal way, you can say as follows. Alice writes an integer n in her diary, which maybe I'll call A. So her diary has possible values from 1 up to n. She writes n in her diary. Then she sends the integer n to Bob. Then Bob writes n in his diary, which I'll call B. Unfortunately, in the lecture, I'm going to write N for Bob's notebook. B was the main system in most of the lecture, so I don't want it to shift it to B being Bob's diary. So now the contents of Bob's notebook and Alice's diary are identical, and therefore the mutual information between the notebook and the diary is log N. Log of capital N, the number of possible values. And that's equal to the number of bits of information that Bob can get when he receives the message. Now we're going to do a quantum version. In the quantum version, Alice sends Bob a state, possibly mixed, of a quantum system with an n-dimensional Hilbert space. For example, it could be, Alice could send to Bob a particle of spin j equals n minus 1 over 2. It has an n-dimensional Hilbert space. So how many bits of information can Alice convey to Bob by sending an n-dimensional quantum system? Well, first let's describe a classical strategy. One strategy that doesn't exploit quantum mechanics is to pick a basis. Okay. The trouble is I want to call this quantum system B to match with the rest of the lecture, and that looks like Bob's initial. I wish I'd planned better and given Bob a different name that didn't start with the letter B. That would have been better. Alice picks a basis from 1 up to n of system B. So she writes n in her diary, and then she sends n to Bob. And then, so in this scenario, Alice and Bob are allowed to have a prearranged code. So when Bob receives the message, either classically or quantum mechanically understands it. So here, the prearranged code is that Bob is supposed to measure on the same basis Alice used. Bob will get one of n possible answers, and therefore Bob gains log n bits of information. Stated in a fancy way, you would say that Bob measures the value of n and writes the answer in his notebook. So in the end, capital N is also a bad name because it's the number of states. I'll call it S for simply because it's a letter I haven't used. S is where this recording device that Bob uses. So Bob measures the value of little n and writes that in his recording device S, and then the mutual information between Alice and S will be log n, just as it was classically, because here Alice and Bob didn't exploit quantum mechanics, treated the quantum system as a classical system with n possible states, and did whatever they would have done classically. Now, now let's instead discuss a general quantum strategy. So Alice has a notebook of any size. W. And she writes n in her diary in W. Oh, sorry. I called it a diary. So, well, okay, doesn't matter. Alice has a notebook of any size n, so I've called it A. So in Alice's system A, she picks the state n. And then if she picks the state n, she sends the density matrix rho n to Bob. So unlike the classical case where there were only capital N possible messages Alice could send to Bob, in the quantum case, she can send any density matrix on a capital N-dimensional Hilbert space to Bob. So the number of possible messages is unbounded in the quantum system. But, but if there are many of them, Bob will have trouble distinguishing them. So anyway, we want to put an upper bound on how much Bob can learn from this. So the density matrix, well, let's say that Alice wants to send a message n with probability Qn. So the density matrix of Alice's notebook and also the system she sends and this is the message. Well, with probability Qn, Alice has written n in her notebook. And then she sent some density matrix rho n of system B in the message. Now, Bob is supposed to extract information from this. Well, what does it mean to extract information from this? What's the most general thing Bob can do? Well, the answer will be to apply a quantum channel in some sense. But before I do that, I want to say that we studied density matrices like this before. I introduced them a few lectures ago, and I called it a classical quantum density matrix. And we calculated the mutual information between A and B in that type of density matrix. And it was equal to the sum of, it was equal to the entropy of the sum of Qn rho n minus the sum of Qn times the entropy of rho n. So in a previous lecture for this kind of density matrix, we computed the mutual information between A and B. And the important thing here is that since entropies are positive, this last term is negative. So this is equal to or less than the first term. And that's equal to or less than log n. Because the entropy of any system on a n-dimensional Hilbert space is at most log n, as you'll prove in, well, the first homework problem, actually. So the mutual information at the beginning between what Bob receives and what Alice had in mind is at most log n. And we want to prove that that's, but this is a quantum mutual information, and we want to prove that that's an upper bound on what Bob can actually learn. Remember what I told you makes me unhappy about the formal quantum definitions is that it's not clear what they really mean physically. And here in a special case, I'm going to explain what it really means physically. Namely, Bob receives his part of this density matrix, extracts some classical information from it, and we want to show that the classical information that Bob extracts is actually bounded by this quantum mutual information. Well, what can Bob do? Well, he supplies an auxiliary system well, maybe I'll call it CM. C is some quantum apparatus, some apparatus, so some experimental equipment. And M is his measuring device. So the auxiliary system, which consists of any equipment he'll use in his lab and also his measuring device, starts out in some density matrix. So the combined system consisting of Alice's diary, the message she sent, Bob's laboratory, C, and his measuring device, M, is in this kind of measuring density matrix. But tensoring with some other system doesn't affect the mutual information. So the mutual information between Alice's notebook and the combination of what she sent, B, Bob's equipment, C, and his measuring device, M, is the same as the mutual information between A and B, so it's equal to or less than log n. Then, what can Bob do in his laboratory? All he can do is to apply a unitary operation to BCM. He can apply a unitary to BCM. That will give no change in I. Then he can forget BC. So forgetting BC is called making a measurement. Okay. The unitary has affected the measurement device. So in the final state, the measuring device is in some state that wasn't uniquely determined a priori. What it means to make a measurement is that in the end, you look at the measuring device and forget about the system that you measured. So that's a partial trace. So if I call this rho A, B, C, M, that just maps rho A, B, C, M to the trace over BC of rho A, B, C, M, which is rho A, M. Now, if M is a good measuring device, that means at the end of the experiment, it has a diagonal density matrix in some known basis. So now we're in a classical situation. And in the final, at the end, there's a class. Okay. If the measurements, we're really out of time. I apologize for running over today. I might have to take a few minutes Thursday to pull together the loose pieces. But if the measurement succeeded, that means at the end, both the density matrix on A and M are both completely diagonal, and you have a classical probability distribution, which describes classically the information that Bob gets about Alice's system. And what the construction is supposed to have showed you is that the classical information about Alice's system that Bob gets at the end is no more than log n. So first, that's an interesting fact. Quantum mechanics didn't let you do better than you could do classically by the classical strategy. But secondly, and equally important, we needed monotonicity of relative entropy to show that. So I apologize for running over, and I don't even know if I should take a minute for questions. Maybe if there's a very quick question. Yes? Well, we don't want to trace out A because what we're interested in is how much Bob learns about Alice's system. So the correlation between Bob's measurement device and Alice's system is what we're interested in bounding. I'll try to tie... Okay, I think I made too much of a mess of this at the end. I'll try to explain it a little bit better at the beginning next time. I think there's another class, so I think we can't stay longer, but if anyone wants to ask questions privately, you can do so.